Kia ora. Welcome to lecture 3 of week 6. Robert McLaughlin here. Today we're going to be looking at boundary value problems, so we're still on higher order linear differential equations. The difference between a boundary value and problem and an initial value problem, which is what we've been doing until now, is that the pieces of data you're given to get a unique solution are given at different points. So one value of y is given at x0 and another value of y is given at x1, two different points. And until now we've been giving a value of y at x0 and a value of y prime at x0. Two data values at the same point. The boundary value problem is different. The values of y are specified at different points. Here I've got a second order differential equation. Now if you can solve that second order differential equation to find the general solution, then satisfying the boundary values as well would not be difficult. You would just substitute the boundary value in, the boundary data in, solve for the coefficients in the general solution, and you're done. And I will do an example like that in a second. But I want to start with something slightly different. It's a differential equation with some boundary values at x equals 0 and x equals 1, but with an unknown coefficient or an unknown parameter, lambda. Now before, when we had parameters in the differential equations, like the mass or the spring constant, they were assumed to be given, either given values, given numbers, or arbitrary numbers. This is different. We're actually going to try and find the value of lambda. And the question says we're looking for non-zero solutions. Now that's very important because y equals 0, that's always a solution for all lambda. If you take the 0 function, y equals 0, it satisfies the differential equation and it satisfies both boundary values. It's always a solution. So we want a non-zero solution. Something that starts at 0, ends at 0, but isn't 0 in the middle. We don't know what it is yet. So let's have a go and see what we get. It's a constant coefficient equation. So the indicial equation is m squared plus lambda equals 0. M squared equals minus lambda. M equals plus or minus root minus lambda. So I see immediately that it's going to depend a lot on whether lambda is positive or negative. So what I'm going to do is to break the different possibilities for lambda down into different cases. And case 1 is going to be when lambda is negative, because then minus lambda would be positive and I would have real solutions. And to make the algebra come out a little bit easier, I'm going to put lambda equal to minus k squared, where k is a positive number. Because then m would be plus or minus root minus lambda, which is plus or minus k. And that means my solution would be c1 e to the kx plus c2 e to the minus kx. And remember that I'm seeking the value of lambda, which means I'm now seeking the value of k, because lambda is minus k squared. So I plug in the boundary data. I'll overlap this a bit. I have to satisfy that y of 0 equals 0. That means 0 is equal to, well, e to the 0 is 1, so I get c1 plus c2. Well, what's happening to the pen there? Y of 1 equals 0. Plug in x equals 1, I get c1 e to the k plus c2 e to the minus k. And I want a non-zero solution for y, so that means c1 and c2 cannot both be equal to 0. Of course, c1 and c2 equal to 0 is a solution, but that's not the solution I want. So I solve the first equation for C2. I substitute it into the second equation. I get 0 is equal to C1 e to the k minus C1 e to the minus k. That is C1 e to the k minus e to the minus k. And the question is there a non-zero solution for C1? Because if C1 is 0, then C2 is 0, and I've just recovered the 0 solution. So that means the only way I can get a non-zero solution is if this one is 0. So is there a value of k that makes this thing here equal to 0? Well, if I graph those two functions, e to the k looks like that. E to the minus k looks like that. They're never equal. E to the k minus e to the minus k is never equal to 0 when k is positive. So I did all that work in case 1, and all I found was that there are no solutions when lambda is less than 0. So I carry on. Case 2. Lambda equal to 0. That means the roots are 0 and 0. I have a repeated root, which means y is equal to C1 times e to the 0, which is just 1, plus C2 times x. Are there any values of C1 and C2, which gives a non-zero solution? Plug in x equals 0, I get y of 0 equals 0 equals C1. Plug in x equals 1, I get C1 plus C2. And you can see there's no solution because the first equation says C1 is 0. Plug into the second equation, I get C2 equals 0. I get C1 and C2 equals 0. So I get no non-zero solutions. But in case 3, when lambda is positive, I run out of space. I will get a solution. So now we look at case 3. Lambda positive. And this time I'll put lambda equal to plus k squared. That m is going to be plus or minus the square root of minus k squared, which is plus or minus ik, which means that y is equal to c1 cos kx plus c2 sin kx. Are there any solutions that satisfy y of 0 equal to 0 and also y of 1 equal to 0? Well, let's see. Y of 0 equals 0. Plug in x equals 0, cos of 0 is 1, sine of 0 is 0, I get c1. Plug in x equals 1. Well, I already know that c1 equals 0, so I'll skip that term. I get c2 sine of k. Are there any values of k that make this term here equal to 0 so that c2 can be non-zero? Yes. Non-zero solutions if sine of k equals 0. Gosh, sorry about the pen. I don't really know what's happening there. So the solutions are k equals any integer multiple of pi. Those are the roots of sine k equals 0. And the solutions are y is equal to, well, c1 had to be 0, but c2 can be anything. So the solution is any constant c2 times sine of n pi x. What do they look like? Well, it depends on the value of n. N equals 1, 2, 3, and so on, any integer. When n is 1, I get a solution that starts at 0, ends at 0, and looks like sine. That's sine pi x. When n is 2, I get sine of 2 pi x, which looks like this. When n is 3, I get sine of 3 pi x. So I get an infinite family of solutions, one for each value of n, and they have more and more oscillations. The second example is a little bit different in two ways. It doesn't have this unknown parameter lambda to be determined. It says the temperature U of R in a ring shape, let's try and draw a ring. So the inner radius is 1, the outer radius is 2, and the temperature is a function of radius only, and it varies with the radius according to this function U of R. And so for example, it's a metal washer, and the temperature on the inside is going to be held at 10, the temperature on the outside is going to be held at 100, and I need to find how the temperature varies between inside and outside of the ring, and it tells me what differential equation is. Here it is here. It's a boundary value problem. So how am I going to solve this boundary value problem? Well, I want to recognize various ways you could do it, but I want to recognize it as a Cauchy-Euler equation. If I multiply both sides by r, I get r squared u double prime plus r u prime plus nothing equal to 0. There are other ways to solve it as well. I'll refer it back to our previous lesson. That means the indicial equation is m minus 1 plus m equal to 0, or m squared equal to 0. It's the double root case. That means the general solution is y is equal to c1 x to the 0 plus c2 x to the 0 log x. Well, x to the 0 is 1, so this is just equal to c1 plus c2 log, oops, I didn't mean x did I mean r, my independent variable is r. Let's just fix up that little mistake. Okay, so I found the general solution. Now I have to impose the boundary values. Really demonstrated poor behavior here. I've used completely the wrong names for my variables. Let's change that one to u. Let's write that out again. U of r is some constant plus another constant times log r. And here are the two boundary values. U of 1 is 10, U of 2 is 100. Write them out again. If I plug in r equals 1, I get 10 is equal to c1 plus c2 log 10. If I plug in r equals 2, r is equal to 1. If I plug in r equals 2, I get 100 is equal to c1 plus c2 log 2. Now log 1 is equal to 0, so this simplifies. So I get c1 is equal to 10. Second equation now says 100 is equal to 10 plus c2 log 2. So that means c2 is equal to 90 over log 2. So I get the heat distribution, temperature distribution, U of R is equal to 10 plus 90 over log 2 times log r. So there's the solution. U of r equals 10 plus 90 over log 2 times log r. I'll have a go at sketching the graph of that. R goes from 1 to 2. Temperature goes from 10 at this end to 100 at this end. And in between it follows the course of a constant plus 90 over log 2 times log r. Something like that, and I really have no idea what the pen is doing to do those little bumps there. That is very, very strange and annoying. That's my attempt at the graph of the solution. Thank you.